Swayam Prabha. Digital India. Educated India.
Good morning. So, what we do today? Well, again what I said before, we will be talking about the cycloaddition reactions, and in the first few minutes, maybe roughly about 15 minutes, we will talk about the definitions, the notations, and then just a bit of a revision. So, what we did last time. Okay. Just to clarify the definition of cycloaddition, I think all of you know what is the meaning of cycloaddition. The name implies this. What is the meaning? Cycloaddition is a chemical reaction, right, where two components add. No, it could be more, it could be 3 also. So, at least 2 components add to form an adduct, which is adduct, or which is known as cycloadduct. Means all the number of the atoms of the starting materials is preserved in the product. That means, there is no change in the molecular formula in going from the starting point to the end product. Okay, that means, no small molecule or big molecule is being expelled or excluded from the product. That means, the total number of atoms involved in the starting materials would be same as the total number of the atoms in the product. That is number 1. Number 2, the definitions could be these cycloaddition reactions are those reactions in chemical term where 2 new sigma bonds are being formed, at least 2 new sigma bond. There are cases where you can have 3 or 4 sigma bonds are being formed, but normally 2 sigma bonds are being formed. Okay. So, that means that covers all kinds of cycloadditions you have come across so far, and the notations are little different in many cases. In synthetic chemistry there is notation, and mechanistic chemistry there is different notations. Okay. The popular ones most of you know. I think when you talk about the most popular one is 4 plus 2 cycloaddition, right, 4 plus 2 cycloaddition reaction. 4 plus 2 cycloaddition reaction, and next popular one 3 plus 2 cycloaddition reaction. So, we go on like this. Then there are of course, the little less popular is 2 plus 2, then there are 4 plus 3, then 5 plus 2, and then what else? Anything else? There is also, there are quite a few more, and so what do? We name them higher order cycloaddition reactions, Okay. But at the same time, you have to know what these numbers mean. This is important. When you do the simple notation, actually these when you talk about this notation in this class, we talk about the synthetic chemistry. In synthetic chemistry, these numbers actually represents the number of atoms of the reacting chains, not the number of the atoms of the starting material, number of the atoms of the reacting chains. Okay. For example, all of us know, right, this is the typical Diels-Alder reaction, and the product here. So, here is a cyclohexene, and this is the new sigma bond, and this is the new sigma bond. So, total number of the atoms on the left hand side is equal to the total number of the atoms on the right hand side. Everything is okay. 2 new sigma bonds are being formed, cyclic compound is being formed, and this 4 actually denotes the 4 1 2 3 4 5 6. That means, this 4 refers to the number of the atoms, and but then if you are talking about the mechanism of the pericyclic reactions, then this 4 actually refers to the number of the pi electrons, the number of the pi electrons. Let me give you one more example that would clarify. You let us say 3 plus 2 cycloaddition reactions. I think all of us know what it is, ozone, and then if you react with olefin, first it forms the mole ozonite, and right, mole ozonite. So, what is this? How do you classify this reaction? This reaction is classified as 3 plus 2 cycloaddition reactions, 3 plus 2 cycloadditions. Alternatively, okay, we will talk about the alternative ones, but in this case 3 refers to the number of the atoms of the reacting chain 1, 2, 3, and in this case the other one is 2. But in mechanistic chemistry, or you can say when you talk about the mechanism of the pericyclic reactions, this should be considered as 4 plus 2 cycloaddition reaction. Reason being, there are 4 in this skeleton you have component, you have 4 electrons, in this component you have 2 electrons, that means we count the number of the electrons. Okay. So, these are the definitions, and then there are some other things like this is a very next to 4 plus 2, 3 plus 2 also is very important. It has another name, I do not know whether you know or not, it has another name. What is the name? 1,3 dipolar addition, in 1,3 dipolar cycloaddition, 1,3 dipolar cycloaddition reactions. This is just because the other thing is always 2 electron component. So, in most cases this is a very versatile method. And so, in the last class actually what we talked about? We talked about both the reactions 4 plus 2 and 3 plus 2. So, what we do today, we will have little bit of the assorted examples to show you the power of these reactions, the nature of the products, and also you have to mentally work out some of the answers of the problems I gave you here. Okay. And then when I talk about these reactions, there are 2 important points. The first point is that the heterocyclic can be used as the dienophile or diene, that is important. Okay, there are 2 ways, that means you can make use of heterocycles and you can build up the heterocycles by cycloaddition reactions. That means cycloaddition reactions can be used in 2 different manners. Okay. In one case they can be component of the cycloaddition reactions, other case the result of cycloaddition reaction could be heterocycles, that means you can construct them. Okay. And so, if you go to my note previously, you will just see let us say most of the examples there you can work out, and I will just pick up only one of the examples where this heterocycles a heterocyclic molecule has been used to construct an heterocyclic molecule. Like this one is a case in the synthesis of vitamin B6, where you start with a compound called name oxazole. Good. Oxazole is now you have a substituted oxazole, and then if you react with this diester malleate. Okay. And in my class E stands for actually an ester group, normally aliphatic ester, methyl ester, ethyl ester. So, then you use a Lewis acid, and in this case neodymium triplet. So, you get directly this pyridine nucleus. Okay. By the way, if you have any questions, you can stop me, interrupt me, ask questions. It is not a matter, okay. It does not interfere this recording here. So, and now you see, now you have to basically you have to try to read this equation. What is this equation? You start from a heterocycles, 5-member heterocycles, azole, then do a Diels-Solder reaction, and mentally you have to work on the intermediate. The intermediate would, that means pericyclic reactions, the components remains as it is without any rearrangement, only a connections are being made, and through the ends though. when the cycloaddition reactions takes place, actually you have to concentrate on the ends, not in betweens. Okay. Then you have to reorganize the electrons. Then the rest of the things remains as it is, and then this you have this ethyl group here, and then you can go on and do this sort of rearrangement eventually. So, this is that means, it is a case of an heterocyclic being used for the construction of the heterocycle. Actually, it shows the dual purposes of heterocycles, cycloadditions in heterocyclic chemistry. So, likewise, there are quite interestingly, there are many examples. I will just for giving you some of the ideas to how the heterocycles are used. So, what I will do, I will pick up a few selected examples. Let us say this one is a very popular example in heterocyclic chemistry. Sometimes it is called Bogar chemistry. Bogar means Del Bogar, a scientist in California, a Scripps Research Institute. He exclusively works on tetragen molecules. Tetragen molecules. When I say tetragen molecules, you must have something in your mind. What does it mean? It means tetragen molecule means you have 4 nitrogens, of course, and agene means when I say let us say when I say Joel means basically a 5 membered ring. So, agene means, so you have a 6 membered rings. So, okay. So, just I will give you an example how it works, and this is a molecule here, and you see this is actually exclusively used by Del Bogar. There are many other who have used, and once again I write E here. If you mix up with and let us say a triple bond. So, if you do not know actually what will happen, then it is very difficult to actually make out, very difficult to make out. But since we know that tetrazene is a diene, so what happens actually, it first undergoes Diels-Alder reactions. So, Diels-Alder reaction. So, what you do, you first find out the ends, identify the ends of the diene part. So, in this case, let us say the top part or sorry or the bottom part is the diene part. Okay. So, that means this end would add to the electrophile sorry dienophile. In this case, it is this, right. So, then rest remains as it is, and so then you reorganize the bond according to the valency. So, you get to this sort of compound here. So, that this is basically called Diels-Alder adduct, okay, or 4+2 cycloaddition reaction, right. So, what next? What next? Actually, it does not stop here. If you keep on heating this reaction mixture, eventually one can on nitrogen, one can see there is a nice driving force here. What is the driving force? The driving loss of nitrogen, and so what you will find? You will find again now a diazine. It is a diazine product. So, E here, and then AR and AR. Okay. So, once again this is although it is a heterocyclic compound, but you are making a heterocyclic molecule by the application of the cycloaddition reactions. So, very useful reactions, and this is now this has a name also. This sequence also has a name, and some of you probably know because if you just again go back, this sort of reaction is known as Alder-Rickert reaction, Alder-Rickert reactions. Okay. What it means? So, basically it is a combination of Diels-Alder reactions and Ritto-Diels-Alder reactions. It is a combination of Da plus, all of you know, Ritto-Diels-Alder is abbreviated as RDA. Okay. So, In fact, we are planning to make use of these reactions in our lab, and the beauty of this reaction is that this tetragene can be made from a very simple molecule. Can you guess by looking at the structure? Very simple molecule. One of the tetragene, the starting material, the starting material. So, that means it is a very highly symmetric molecule though. So, in organic chemistry, most of you know, the identifying the right starting material is very important. So, that means you have to have a nice correlation with the structure with the available starting material. In fact, towards the end of the class, I would summarize probably the available nitrogen sources. Available nitrogen, not in nitrous acid, potassium nitrate, etc., what we need for other things, but it is the nitrogen source for the synthesis of heterocycles. Can you name any very quickly? I mean, you have sufficient background in heterocyclic chemistry. Can you name 5 different nitrogen sources which supply nitrogen for the synthesis of heterocycles? Urea. One of them is urea. The other 5. I require only 5, not many.
Ammonia, hydrogen.
Okay, hydrogen I will accept. Ammonia accept, fine. 2 more. Nitroso compound I will take, but not okay, they have limited use. Okay. So, like this, so if you summarize, you will find that heterocyclic chemistry is very easy. In fact, one of our teachers in the science college, Professor A.K. Sen, probably many of you do not know, and I still regard him, he is still alive, and he was also at IIT, our department, as a faculty member, and he used to teach like this only. Okay. Identify, you make a synthetic pool of the nitrogen compounds, from there you pick up and try to correlate with those pools with the final product and see how synthetic, because heterocyclic chemistry many times, many occasions you will find is very boring. Okay. Same thing again and again, and this when it is done, it is so easy, and and there is no stereochemistry, all the molecules are flat, but they are useful. Okay. So, we will any case, but as you go on, we will just find out the kinds of the nitrogen sources you need for constructing heterocyclic molecules. Okay. And so, coming to the answer, it is nothing but glycine ester. If you glycine ester add nitrous acid, what happens? Let us say you have ethyl glycinate. If you go to the back slides of my lectures, you will find the answers there. Ethyl glycine, then treat with sodium nitrate HCl, you get the ethyl diazoacetate. Okay. And ethyl diazoacetate under basic conditions undergo dimerizations. So, that means let us say this portion comes from the glycinate, right. Nitrous acid gives one more nitrogen. So, you get this diazoacetate, and then if you dimerize them, you get to this compound. Okay. It is quite easy to make, and then aromatize. So, so these are the things actually we talked about, then we have shown the applications, but what we do today, just a little bit of the variations of the Diels-Alder reactions. Variations of the Diels-Alder reactions mean when you talk about the regular Diels-Alder reaction, some people try to say this is called C Diels-Alder reaction, CDA means carbon Diels-Alder reactions. So, then of course, there is no nitrogen Diels-Alder reactions. So, what we call HDA. So, HDA in this case we call hetero Diels-Alder reactions. So, there are many of you, like say we have already shown you RDA. So, that means there are plenty of adjectives, right. In this case it is retro Diels-Alder. Any other? These are all names organic chemistry almost regularly used, called IMDA. IMDA is a very useful reaction. I will give you more examples actually today. IMDA actually intramolecular Diels-Solder reaction. So that means intramolecular Diels-Solder reaction. So likewise there is one more. So one more is there. IED Diels-Solder reaction. What is this? Inverse so all of you know then, okay. Basically so these are all different kinds, okay. There are different kinds of reactions, and that means if you have a known reactions you want to extend it to today we talk about a little bit of this example of this HDA. HDA there are actually 3 different versions. HDA means one of these could be, that means you put heteroatom. So this is one of the case. In this case you have placed nitrogen in the dienophile. There are other possibilities, there are so many other possibilities. Let us say you have another possibility that you place the double bond nitrogen in the diene component, and then of course you change the positions, and then you can see all kinds of things. Of course this all of you can guess what could be the product would be a cyclic one, and then with two new sigma bonds and the electrons organized accordingly. So like this I think all of you can write the structure. So this word would give you see here in all cases the end product is or end products are heterocycles, right. So now question is I mean in principle everybody can write this, that is not a big problem, but what you need to know that which one is more feasible or which one is more likely to take place in the lab, that is important, and or what are the problems or drawbacks in this sort of reactions. Any guess what could be the problems? That is you have to you have been sufficiently knowledgeable about this chemistry. If you look at this is also it has this in this particular case this is basically a class belonging to HDA, heterodiel-solder, but it has a name also. It has a name also known as immunodiel-solder. I think immunodiel-solder means basically you guess that Schiff's base. It is not Schiff's base diel-solder, we call immunodiel-solder. And if you are little careful then it has also a name associated with this reaction. What is the reaction is called Provorov reaction. It is a Russian name of course. So Provorov reaction. That means Provorov reaction is basically a 4+2 cycloaddition reaction used or utilized for the construction of heterocycles. We will have few examples. But before I go to the next one, you have to just sit down and think about and what are the difficulties actually. In fact, I was not knowing till my friend started doing work on this immunodiel-solder reaction in 1980 at Rensselaer Polytechnic RPI, and when he started making azadines. Any idea what is the, what could be the problems? See, many of you have been studying the biological chemistry, right. In biological chemistry there are again only a handful of reactions, not many reactions, but one of the fastest possible reaction is what? First reactions other than acid base reactions. Hydrogen? No.
Nitrogen evolution.
From where? Biological organic reactions, bioorganic reactions, let us say. This is important. If you go to the, and this actually gives, this concept actually gives rise to many important reactions. If you can identify, if you can rank the reactions in terms of the activation energy, We do not call activation energy, or we do not give the numbers, but we can say this is faster, this is slower, this is slowest, this is fastest, that kind of thing we can do. Like one of the ways to look at any organic reaction is that acid base transformation. Okay. Then next one is the isomerizations, possibly it could be one of the very first reactions. Actually, many of you probably do not know, Schiff's base formation even in water is one of the very first reactions, very first reactions. So, and this concept has given rise to many multi-component reactions. See, in most of the multi-component reactions, you must have heard, actually one of the very first point is basically the Schiff's base formation, and we will see some of the reactions here. So, what does it mean? It means that Schiff's bases are not very stable. Again, I often ask these questions in research seminars. Many times many research scholars, they will show, okay, this Schiff's base has this proton here, this proton here, this IR value here. I said, how did you purify? He said he did not purify. Some people without knowing, he said, no, we chromatograph. You cannot do it. You cannot do the chromatography on the Schiff's base, because on silica gel it breaks down. I mean, maybe in starting material was very pure, when you pass through it silica gel, half of this is so fast. That means that's what you have to know. So, that is basically drawback in this azide-Diels-Solder reactions, azide-Diels-Solder reactions or imino-Diels-Solder reactions. So, you have to have some rough idea about that which one is more feasible. We can write 3 different versions, especially the one on the right is not very popular, but again without isolation you can engage them in the Diels-Solder reactions. So, likewise we will have a little bit of examples, for just very quickly. Let us say you have an aromatic compound. Now, this is again a Schiff's base here. So, benzaldehyde and aniline. Then we took let us say we take cyclopentadiene. So, what can you expect out of this? Let us say as if we do not know anything about these reactions. In this case, because the compounds are aromatic, so the Schiff's base is fairly stable. In fact, you can isolate. You can just do the reaction, just boil the two, do not do anything, just boil the two, they will come out from the reaction as the solid. Then if put this, nothing happens. Well, under the presence of Lewis acid, in this case indium chloride. So, what is expected out here is basically Lewis acid. Now, you have to independently predict what could be the outcome of this reaction. Let us say, since I have been talking about the Diels-Solder reaction, etc., you can think about the Diels-Solder reactions. Suppose, let us postpone the thinking to Diels-Solder for some time, but let us think otherwise. What do you expect? If the Schiff's base is not sufficiently reactive, you can expect a dimerization of the cyclopentadiene, because at room temperature it dies. So, that means you have to have some reference. That means this is the reference knowledge. The cyclopentadiene is sufficiently stable at room temperature, but under a certain time at room temperature it dimerizes. So, if that is so, that means you can guess that butadiene would be fairly stable. Okay. So, likewise okay, and the product here and product here is basically a Diels-Solder product, and so in this case one of the double bonds of these I think something is wrong here, my note, right. One of the double bonds, that means of the benzene ring, this aniline part would be engaged in the Diels-Solder reactions. So, that means 2 and plus 2 and this 2, right. So, that means so for this one, that shifts best part and one of these double bond of these would undergo reactions, and eventually that means you will have a kind of a double bond up here, right, and but all of us know that this cannot be stable. So, it undergoes isomerization and isomerization. So, what you will have a real polycyclic real polycyclic, and also you can say quinoline derivative is being formed in this. And as usual the stereochemistry in Diels-Alder reactions or in all kinds of pericyclic reactions you will have these stereochemistries are well defined. I mean the cis addition and all these things. And so, likewise I will just give you one more example. This is a again a Schiff's base. Now, if you react this, you see here ethyl vinyl ether. So, what do you expect? See, we have been talking about this heterocyclic chemistry etc., 4+2, but you have to once again you have to forget about this and start from the very scratch. If we have two components, I mean this is I talk about in the also in my synthetic chemistry class also I talk about when a reaction is being done or rather or is proposed or you are supposed to predict the outcome of a reaction. Where do you start from? You just classify them in 5 different categories: acid base reactions, light catalytic reactions, thermal reactions and oxidation reductions, not many, right. Do you remember? No, you do not remember. Okay. All organic reactions, just name a reactions outside this category, either acid catalyzed, base catalyzed, light, heat, oxidation, reduction. Any other reactions known? You can say isomerization. Isomerization is a reaction, but it is a thermal reaction. It is a thermal reaction, or it could be base catalyzed, it could be acid catalyzed. All these pericyclic reactions, all pericyclic reactions are thermally allowed or photochemically allowed. So, no, that is it. So, that means when you are not given any option here, okay, what do you expect? It is a thermal reactions. Okay, but in this particular case, the example is this answer is BF3 etherate, BF3 etherate. Okay, BF3 etherate. So, acid. So, acid catalyzed basically acid catalyzed reaction. Acid catalyzed means normally if you do not have any nucleophile etc., so thermal reactions are possible. So, this is Diels-Alder is a form Diels-Alder or any thermally allowed cycloadditions are possible. In this case, of course, there is a Diels-Alder, but you have to know that double bond of an aromatic system also can participate in the Diels-Alder reactions. Did you understand what I say? Probably you did not. Okay. Let me just give you this reference reaction, then you would be able to just heat it. What do you expect? This is the reference reaction for what I said, that although deep seated double bonds, they are seated within this aromatic system, they can also come out and react with the dinophiles to form this Diels-Alder adduct. If that is so, that means that I am talking about this double bond actually. This double bond belongs to the aromatic systems, yet it is reactive as a double bond of the diene system. So, product would be a Diels-Alder reaction. It is a product of the Diels-Alder reaction. In fact, such reactions are used in steroids. So, it is right, and then what? Then isomerization. So, this is just basically an example. This is an example where a double bond of an aromatic system is participating in the Diels-Alder reactions of a diene, that means it forms the diene component. That is what is happening here. In this previous example, what you see, this double bond is basically part of a diene system. So, this double bond and this double bond together, they are double bond. Now, next important thing, why did I choose ethyl vinyl ether? I could have used normal dienophile. Normal dienophile is ethyl acrylate, acetylene dicarboxylic acid as ester. So, like this, but instead of choosing those malic anhydride, but alpha beta unsaturated ketones, instead of choosing those Michael acceptors or the dienophiles, I have chosen here ethyl vinyl ether. Guess? I would say differently, little differently, not specificity. Okay.
This is an example of inverse.
Right. Basically, that is what you have to see. I think all of you have gone through, at least those who are our MSc students have gone through so many physical chemistry courses, right, including those who have come from Calcutta University. I know they must have studied the quantum chemistry quite a bit, quantum chemistry. Okay. So, just very quickly, now that you have to, because what I am trying to say that we do a lot of things, but you have to screen out some of the things. Okay. You have to leave something, you have to gain something. So, you have to choose rightly, selectively. For example, let us say, how many of you know, let me see, how many of you are able to do the calculations of this one, these two, only 4 electron system. Who would be able to calculate the HOMO of this and LUMO of this? Raise hand. I know all of you have, our MSc students have gone through 3 or 4 quantum chemistry courses. Kaushik, bolo Kunal, আর কি মাঝি জানো, সিদ্ধার্থ মাঝি, বলো বলো। Okay. See, what I am trying to say, how do you calculate this HOMO energy or LUMO energy of butadiene? You just sit down, you do not have to stand. So, that is something, that means those courses are useless, it seems like. What I am trying to say, you have to know, why do you study all these things?
So, by
No.
considering the
How much time would you take to do the calculation? No, how much time I said? If I give you this problem to now, how much time you will take to complete this HOMO LUMO calculation of this one? Now, okay, tell me what is the value?
So, by considering the energy value
So, I want a number.
alpha plus 0.61.
I want a number. That is what I am trying to say. Okay. How much time would you take to calculate HOMO energy and LUMO energy of butadiene? Okay. Just very quickly, I mean, although we do not do this practice, right, for organic chemist the practice is little different. Okay. Like this, when you go to this one, if you replace CH2 by nitrogen, let us say, just give me the answer. If you put the nitrogen there, is the HOMO energy would be increased or decreased with respect to butadiene? By how much? It will decrease. That is the important point you have to remember. That means that HOMO energy is getting decreased. So, that means your LUMO energy, sorry, HOMO energy of, I mean, dienophile, so called dienophile, should be increased. That means there should be a balance basically. These energy gaps should be as minimum as possible, then they will undergo reaction. Okay. If it is decreased, then that should be increased and vice versa, and so you have to have a compatibility. So, but we do not talk about all these things, but in the back in the mind we just remember that activity is, energy is reduced. Okay. So, that can be compensated by increasing the energy of the 2 pi electron part. In this case it is the ether, and most of you probably know this vinyl ether is an electron rich system, because of the lone pair conjugations with the this pi electron. So, as you rightly said, it is an example of inverse electron Diels-Alder reactions. So, what is the product we will be getting? The product we will be getting and so, after isomerization all these things, so what you will be getting? You will be getting this one, and mind it, in this case, what you see, the ethoxide on this side, it could be on this positions also, right. But once again this direction or the addition to this system is due to this effect of this oxygen lone pair to this system. So, then of course, if you just do a little bit of the synthetic manipulations, normally in this case paratoluene PTSA, paratoluene sulfonic acid, you have to go then okay. So, what you will find, it will give you this reaction known as okay. So, quinoline. So, this particular reaction is known as Povarov reaction. This particular reaction is known as the Povarov reaction. We will continue with this basically this Aza-Diels-Alder reactions or Aza-Diels-Alder reaction or HDA hetero-Diels-Alder reactions, and let me just very quickly go to a very famous reaction. In this case, the reactants are cyclobutadiene and amine, you can say consider to be an aliphatic amine, NH2, and the corresponding salt that is HCl. Amines normally are purified as HCl. Then if you react with formalin, so what you will get, and this is just at a room temperature though, at room temperature. So, what do you expect? Once again, I mean this is within your capability, means if you just think about it seriously, you can tell me the right product, but outcome is very interesting. It is very simple reaction, because it is just mix them up at room temperature in water. Formalin means 30% formaldehyde and water, 35% formalin in water. So, what do you expect?
First imine formation, then
First imine formation. So, that means first you would like to see, that means as I said before, imine formation also requires dehydration, right, but it can be carried out in presence of water, but in the presence of a catalyst. And so, what do you expect? You will expect a this, right. Now, what do you so obviously in this case this one would undergo Diels-Alder reaction, and this would be this nitrogen, and this would be write phenyl and a double bond, that is it. That means cyclobutadiene is now 4 electron component, and this is double electron. So, in this case this is basically a Schiff's base, that is what we talked about, that is there are 3 different variants, and the reaction is pretty well known, very well known. Okay. Now, exactly same way, if you begin with a compound, let us say I will just give you this is a very useful one, that imines and the corresponding Diels-Alder products, because what you end up, you get a nice heterocycles with nitrogen 1. Now, it is a bicyclic one. Now, the double bond can be synthetically be manipulated in different manners. So, you can cleave it, you can do all kinds of things. So, you get a nice cyclobutadiene. So, pyrrolidinone kind of molecules. Let me give you one more interesting example, where you will have cyclohexenone and then and again an amine, again formalin. So, what you see here, the compositions are formalin and little bit of DMSO is in this case added, and the temperature is little high. So, 50 degree. Then something else, one of the other component is S-proline. Okay, so, I think all of you understand what is okay. What are the things? I mean, the way I have written, the formalin is not a reactant, but it is a reactant. It is a reactant. So, what do you expect? Once again, one of the what I said, after acid base reactions, one of the fastest possible reactions is the formation of aminol. See, if you think about the reactions of an amine with an aldehydes or ketone, the very first step is formation of aminol, addition of nitrogen to the carbonyl to form the alpha aminol. Okay. Those are pretty unstable. So, they stay in equilibrium with the Schiff's bases. So, that is one of the very fastest possible reactions in organic reactions. Now, that is what is happening here, and between the two you have all components here, you have an amine formalin. So, what you will find? You will find one of these intermediates would be this nitrogen and the Schiff's base here, right. That means, you have to then look for what? You have to look for something. You have to look for a diene. So, how cyclohexenone is not a diene. Right. So, not enol form exactly. So, what will this proline will form the enamine, that means, the other portion would be in this case this one sorry I think yes. So, this one would be this enamine. Okay. Then now you know that this now you can guess this become diene, and this is the dienophile component, and this become the diene component. So, eventually I must just if you sit down and you can work out this problem at home without much problem. So, eventually what will get? You will get a again a bicyclic system, and it is a ketone, and then you have two methyl groups here. Anything else? So, this is a bicyclic. That means, this diene part would react with this, and mind it, in this case because of this nitrogen, this electron flow would be towards this carbon. This is important also, and this carbon would add to the imine carbon here, imine carbon. So, that determines the regiochemistry part of this one. So, anything else? Vivekananda, anything else? This is important. I am writing, you are writing, that is not a problem. You have to see what are the other thing we would like to convey, what message we like to convey. It is a case of organocatalysis, and the EE is 99%. So, 99%. So, I mean, so there are other reactions maybe. I mean, let us say, I think I would talk about one more reactions in this area. This is a very interesting area, interesting chemistry. Many of you, this is actually it's pretty similar to a kind of a dienophile called diene called Daniszewski diene. Do you remember the structure of Daniszewski diene? It is a diene. What you will see, you have double bond, you have a double bond. What are the features of the Daniszewski diene? What are the features of the Daniszewski diene? it is a bit second position. Second position is occupied by either by nitrogen or oxygen, but normally it is oxygen. So, in this case, and you have the silicon here and this, and the other one is this, and you have a methoxy here. What is the normal example? You have to have a dinophile with the carbons, that is the standard example, but what is known that if you react with again the shift base, the standard shift base, because this is easy to work with, fairly stable, and you can isolate and you can work with. Now, one could have written also the differently or the same thing, right, this, but this is not a feasible. I mean both are same though, but in for the reaction with this one, this orientation is appropriate. Reason being you have again this oxygen lone pair. So, this lone pair of electron directs the electrons to this carbon, and by virtue of this nitrogen electronegativity, these electrons are polarized towards nitrogen. So, you get this one as a positive charge and this one a negative charge, and then combine. So, eventually what you will get, a reaction product where you will have the silicon up here and nitrogen, phenyl, and then you have this O methoxy, right. What next? And silyl ethers, most of you know, are very sensitive to acids. Just if you do the column chromatography or do a little bit of acidic workup, even in ammonium chloride, it will break. So, again this enolized and methanol will come out. So, what you will find? You will find is double bond here and say nitrogen, then phenyl and phenyl. So, what do you get? You get in heterocycle. This is heterocycle now with a chiral center. Okay. And believe me or not, it took so many years to develop a new reactions on the basis of this reaction, and again this is due to the Chinese guy in this case. And what they did, they used once again they used this dinesepskydiene and this aldehyde and then corresponding amine, I don't know, I got surprised to see that such a simple reaction was published in only 2002, not long ago in Orglet. The dinesepskydiene has been known since 1978. That was the first Jack's publication. Okay. But and that the example I showed you before apparently is workable, right? That was also known, but this reaction was not known. Such a simple reaction. What you do here, just as they do not separate them, they do not separately prepare the Schiff's base with aldehydes and amines, just they mix up all the three components together, and that too in a solvent like one of the very cheap solvents, methanol, and no heating, nothing, no catalyst, just room temperature, and what you get? You get the corresponding adduct. One of them, of course, that means what you will basically what you get is 4 pyridone, right? It is a 4 pyridone derivative. It is a 4 pyridone derivative. You will have this one, and then this of course this portion, and then this will have a definite stereochemistry here, and this is stereochemistry, and the other isomer also has been formed, but that is not the major important, that means that ratio is somewhat unpredictable though, but what you can get just if you have a component of this kind, and very easily you can make this simple reactions. That means, you have to have nice formulation, and you could generate a nice actually stereochemistry at two different centers, and many of you know probably this one, this aldehyde is easily obtainable from where? Any guess? Very good. How do you make D-mannitol and sit down, protection and what? You do the protection, then what? Sodium periodate, right? So, that is it. Sodium, you click get, so it is very easy to, okay. And the last reaction, this is a pretty interesting reaction though. I have just one more minute. So, this is just something like again this one, and then you take an aldehyde, then pyrrolidine. I think all of you can guess pyrrolidine. So, just simply I think that is actually catalyst. In this case, this catalyst is little sort of a it is a boron catalyst, here. So, basically it is a Lewis acid kind of thing. Oh, sorry, this I think I made a mistake here. This should be pyrrolidine known, this should be pyrrolidinone. So, what do you expect? Okay, better I write separately. So, this now just like a BF3, in this case it is not the BF3, it is a dibora compound, and just heat it. So, what do you expect? Expectation, right. So, that means first this enamine formation would take. Actually, I should have written CH2 up here, CH2. So, I think better I write CH here, CH2, that is better. So, you first form the enamine. So, in this, and what is the name of this molecule? This is a famous molecule. Sorry, 6 member nitrogen compound. So, name should be gene. So, it comes from phthalic acid kind of thing. So, it is known as thalazine. Okay. And mind it, in this case you get this enamine done, not the shift space. So, you have to have enamine, reason being when you have one nitrogen is electron deficient, you have two nitrogens, it even becomes more deficient. So, that electron deficiency has to be compensated by the other part, and in this case the enamine is electron rich by virtue of interaction of the lone pair nitrogen lone pair with the double bond. So, the end product here after a little bit of this work, what you will find this R, just naphthalene, it is a reverse way now. Heterocycles are being used for synthesis of carbocycles.